My pleasant greetings to everyone, and thank you very much, organizers, for the invite. I am Flora Maitim Yrad from Silliman University, Dumaguete City, Philippines. My presentation is entitled Modified Synthesis of Dextrin-capped Gold Nanoparticles and its Chemistry. In this presentation, allow me to refer to dextrin-capped gold nanoparticles as the gold nanoparticles. The concept of my research is to improve an established method of producing the gold nanoparticles with less time, fewer steps, and minimize equipment. The gold nanoparticles is a novel work at the Nanobiosensors Lab at Michigan State University by Anderson et al. The gold nanoparticles were reportedly applied in biosensing studies, which include detection of dengue-3, Mycobacterium tuberculosis, and Pseudoperonospora cubensis. Although the gold nanoparticles show versatility in some biosensing applications, the synthesis has limitation. One, it involves a tedious pH adjustment in its initial step, and it takes 8 long hours of reaction to complete. And what more, the heating equipment is available in their lab, which is not available in our lab here in the Philippines. So the research aimed to synthesize gold nanoparticles using a revised or modified protocol and to optimize anew the synthesis conditions and characterize the gold nanoparticle products. All syntheses were carried such that the total volume of all the reactants, such as the chloroauric acid, 10% sodium carbonate, and dextrin solution is equal to 50 ml. The effect of temperature, reaction time, and the reactants and each of the reactants were determined to establish optimized reaction conditions. UV spectroscopy, dynamic light scattering, and high-resolution transmission electron microscopy was used to characterize the morphology, stability, polydispersity, and size of the gold nanoparticles. All laboratory works were done at the Nanobiosensors Lab of Michigan State University, and HRTEM and TEM done at Center for Advanced Microscopy at Michigan State University. The difference between the standard and the modified methods are presented in the table. The key features in the modified method are the reversal of the addition in the reagents and the increase in the reaction temperature. Modification of the method makes the synthesis more simple and with accompanied plus factors, such that the need for the pH water, pH meter, and steps were not done or no longer needed. Hybridization oven was replaced with a less expensive hot plate, and most of all, the reaction is reduced from 8 long hours to 1 hour. Figure 1 shows the reduction products and the corresponding spectra of trials M and S for modified and standard method, respectively. For the same reaction composition, trials M and S produce comparable ruby red color colloidal gold. It is noteworthy, however, that the spectral band of trial M is more narrow and showed higher peaks, higher absorbance at 500 nanometer compared to trial S. According to previous reports, narrow band means homogeneous gold nanoparticles, and higher peak means higher concentration and therefore better yield. The chemical reactions involved in the modifications are hereby proposed. The reversal of the reagent protocol involved 3 stepwise processes, which are neutralization, speciation, and reduction reaction. Hydration of sodium carbonate produces hydroxide ions as in reaction number 1. The OH serve 2 functions. First, to neutralize chloroauric acid as in reaction number 2 and provide alkaline reduction reaction as in equation number 3. The increase in the temperature is necessary for the chloroauric acid dextrin system because while dextrin can undergo oxidation under basic medium, the increase in the pH drives the speciation of chloroauric acid to its gold complexes. In the present study, stable red D gold nanoparticles were produced from reaction mixture with sufficient amount of OH for both neutralization and alkaline reduction. Figure 2 shows the reaction products at varied volume of sodium carbonate. Reaction with 0.1 ml sodium carbonate is a case with insufficient hydroxide ions for neutralization and reduction, and the resulting solution gives yellow color with lambda max at 303 nanometer in trial A. Reaction mixture with 0.5 ml sodium carbonate is a case of sufficient hydroxide ions for both neutralization and reduction, and the result is a ruby red, stable gold nanoparticles with lambda max at 520 nanometer. Reaction mixture with 0.7 and 1 ml are cases of excessive hydroxide ions, and the result is a broad band, low absorption at 520 nanometer and even horizontal spectra for 1 ml sodium carbonate. The excessive hydroxide brought about speciation that produces black-purple and black solids precipitate that even cause aggregation. Figure 3 shows the reaction product at different hot plate temperature settings and their corresponding UV spectra. Among the trials, only trial 150 degrees Celsius setting of the hot plate exhibited the characteristic ruby red. 100-degree trial was purple, and 140, 130, and 120 are light red. From DLS measurements, the polydispersity index or the PDI are indicated herein. Based on the PDI classification, 120, 130, and 140 are moderately polydispersed. Trial 120 and 150 degrees Celsius are narrowly monodispersed. Based on these results, since 150-degree hot plate setting gives the maximum absorption at 520, therefore, the experiment indicates that it is optimum to put 150 degrees Celsius for hot plate setting. The absorbance of reaction mixture at 520 was monitored and plotted against time. Figure A shows that absorbance at 520 evolved and increased with time. The absorbance reached a maximum at 21 minutes and make a plateau thereafter. This is consistent with previous reports. Further heating up to 1 hour did not produce significant change in the absorbance at 520 nanometer. And therefore, based on these findings, heating time was set at 1 hour. Figure 5 shows the UV spectra of D gold nanoparticles synthesized at varied volumes of chloroauric acid. The figure shows the reaction products with decreasing intensity of red color. The decrease in the red color intensity correlated with their absorbance at 520. The results imply that the volume of the chloroauric acid determines the concentration of the generated D gold nanoparticles. Therefore, chloroauric acid was the limiting reagent in the reaction. Figure 6 shows HRTEM and TEM micrographs of D gold nanoparticles at varied volume of dextrin. The micrograph reveals spherical shape without aggregation. From HRTEM analysis, it was observed that the diameter of the gold nanoparticle decreases as the volume of the dextrin increases. The different sizes of gold nanoparticles were functionalized with thiolated DNA, and figure 8 demonstrates that 10 nanometer, 9 nanometer, and 7 nanometer D gold nanoparticles produces stable functionalized product. We were not able to functionalize, however, the 19 nanometer gold nanoparticle for the same condition of functionalization reaction. 10 nanometer size of D gold nanoparticles functionalized with DNA was successfully used as label in lateral flow biosensor for the detection of dengue 1. Figure 9 shows some LFB strips tested with the target. As you can see, in negative control gives 1 line, which means negative in LFB test. Positive control using synthetic DNA and RNA targets produce 2 lines, which means positive in LFB test. Stability of gold nanoparticles can be demonstrated in these figures. In figure A, this is a dilution test for gold nanoparticles, and diluted gold nanoparticles showed to be stable up to more than 6 months, while undiluted as is synthesized gold nanoparticles are stable even after 1 year of storage in 4 degrees Celsius. In figure B, this is the functionalized gold nanoparticle, and they are determined or found out to be stable within 1 month. And label gold nanoparticle used in LFB stored in 1 month is stable and still can be used after 1 hour of storage. So table 2 gives the summarized characteristic of my D gold nanoparticles at varied volumes of dextrin. So you have the average sizes of 19, 10, 9, and 7 with different lambda max within the 520 and 517, the corresponding concentration, and therefore it is concluded in this study that dextrin-capped gold nanoparticles were synthesized by modifying the original method. And these D gold nanoparticles were spherical, stable, and monodisperse. The significant reduction in time and accompanied by simplified procedure and equipment makes the modified protocol a better or practical alternative to the old one. I would like to acknowledge the USAID for funding this research through its Advanced Research Scholarship, to the Alu Silhan Nanobiosensors Lab for hosting this research, and thanks to Silliman University for the FADECO Scholarship. Thank you all for listening.